All right, good afternoon, everyone. Welcome back to another exciting installment of Sustainability Issues in Energy. So I expect that most of you all got my Canvas announcement the other day that we are going to start working on Project 2 today. I'll explain, give a little more information on that. Should be an interesting project for y'all. But before we do, we have a little bit more to cover on CCUS, particularly on the kind of on the last little bit of utilization and monetization, which is a big thing. Okay, so this slide up here kind of summarizes, I think, what we were talking about on Monday, which was, you know, how long and how you actually trap the CO2 in the subsurface. And so there's a number of different ways that we can trap CO2, and they range in you know, the security of that trapping. The most secure form of trapping, where's my laser, is going to be mineral trapping. So that is where the CO2 has reacted with stuff in the subsurface to precipitate as a carbonate mineral. And that carbonate mineral is not going anywhere. So that's what we want. And, you know, you can show, models have shown that over time, after you inject the CO2, it spends a little while, you know, trapped or maybe as a residual phase or a dissolved phase, but eventually it will react and precipitate as a mineral. And so the question is how long that process takes. And so, you know, this is an estimate from this classic paper by Benson and Cole from 2008, where they are saying that, you know, it's on the order of tens of thousands of years before the mineral trapping actually becomes significant. But there's some more recent work, particularly out of the group in Iceland that's doing the injection into the basalt there, that suggests that the mineral trapping actually takes over much more rapidly than we may originally have expected. So it could be that you only need to keep it trapped as a gas or a supercritical gas phase for a few decades before really you get the more secure types of trapping mechanisms. So that's actually very encouraging, and I think that we'll probably see more research results on that coming out in the next few years. Okay, now another thing that you can do with CO2 is use it for enhanced oil recovery. And this is a process where once you have produced a sufficient amount of oil from the reservoir that it's not coming out under its own pressure, and maybe you've done a water flood, some type of secondary recovery, that then you look to methods like enhanced oil recovery, which is generally you know, tertiary recovery, to try to get more oil out of the ground. And carbon dioxide is good for this because it is soluble in many oils, not all of them, but many of them. And you can also turn it into a foam, which can be used to push the oil out. So the general way it works is that you inject it into one well, and then you push the oil out to your producer well. And this process takes, you know, years to decades to complete. The first one of these that was done was out in West Texas, in the Wasson Field in, I believe it's in Andrews County, anywhere, somewhere north of Midland. And it's, you know, a very successful and very proven technique in the oil and gas industry. And what's interesting is that there is the potential that you can sequester more CO2 by doing this than you generate from burning the oil that you produce. You know, so IEA says that for 1 barrel of oil that you produce with CO2 enhanced oil recovery, you inject somewhere between 300 and 600 kilograms of CO2. And in burning that barrel of oil, you release about 500 kilograms of CO2. So if you're injecting 600 and only creating 500, you've got a net sequestration of 100 kilograms of CO2 per barrel of oil, potentially. A lot of this depends on the local geology of where you're injecting, how you do the injection, and stuff like that. So there's a possibility that you can have carbon negative oil, but all the stars have to align, so to speak. So the different techniques we have for doing CO2 EOR. So like I said, a lot of the potential CO2 storage has to do with how you inject. There's basically three ways you can do this. The simplest is just continuous gas injection. So that's just represented by this bar here. So over time, you just inject the CO2 and it pushes out the oil. What's more common is what we call a water alternating gas, or sometimes the water will have stuff in it like surfactants or nanoparticles or things like that, where you'll inject the CO2 for a while, and then you'll follow that by a phase where you're just injecting water or water with something in it. And you alternate that. Each one of these phases takes, maybe 6 months to a couple of years, again, depending on the specifics of the reservoir that you're working with. But the nice thing about this is that the water helps if we go back here, the water helps homogenize some of these fronts between the CO2 and the other phases that are in the subsurface. It eliminates some of these fingering phenomena that I think we'll talk about those when we get to the hydrogen unit. But that's why this is done. So this typically maximizes your oil recovery, but it can also do good things for your CO2 storage, because it means the CO2 gets into more of the pore space, so you get better pore space utilization. There's another type of injection called a water curtain injection, and you can either do this with continuous gas injection or with a WAG, water alternating gas. And this is often done in a reservoir where you've got some topography to the reservoir on the subsurface. So if you look at a cross section here, if your reservoir is kind of this dipping sand layer, having the water curtain forces the CO2 upwards. It's not going to go down, it's going to want to go up into the CO2 and eventually out to your producer. So depending on what your reservoir looks like, where your wells are, things like that, you can design your CO2 injection scheme to maximize the oil recovery, which is why a lot of people do it, but also to maximize your CO2 storage. So the question is, how much CO2 does this actually sequester? And there was a really nice study done by Vanessa Nunez Lopez and Moscal, I forget who Moscal is, but anyway, these formerly at the Bureau of Economic Geology, who looked at a field in Mississippi called the Cranfield Project. And this was an area where they got CO2 and they were using it for enhanced oil recovery, but they wanted to see what they could do to get net sequestration of carbon dioxide. And so these are simulation results, but they simulated 4 different injection scenarios. So there's continuous gas injection, WAG, water curtain with continuous gas injection, and then water curtain with WAG. So kind of those 4 combinations we can do. And so what these plots are, this on the x-axis is hydrocarbon pore volume. So this is multiples of the original oil volume in place. So you can see, they simulated, 8 HCPVs of CO2 injections. So that's a lot of CO2. The oil produced, they suggested would be on the order of several million barrels. So that's revenue. But also there are, several million tons of CO2 storage that they, predicted. And in this case, it was actually the continuous gas injection that gave them the most CO2 storage. So again, this has to do with the specifics of the reservoir that they're dealing with. So, you'd have to do some kind of a detailed study like this, but it is possible to get a net storage of CO2. Now, when you think about, is this actually carbon negative? A lot of it depends on many different factors. you can't just get CO2 and inject it into the subsurface, okay? You need to capture it, you need to transport it, you need to purify it. And so all of that requires energy, which may come from carbon emitting sources. And then obviously the oil that you produce is going to be usually combusted for energy. You might use it for petrochemicals, but most of it is being combusted for primary energy. And so as a result, what's really interesting here, so these are the 4 different injection schemes that they simulated. So this red line represents carbon neutrality. And so if you're below that, that means you're carbon negative. So accounting for all the other CO2 emissions associated with the purification and the oil combustion and all that stuff, you would still have net negative CO2 emissions. If you're above this line, that means you have net positive CO2 emissions. And what's really interesting is that regardless of the injection scheme, they showed that for the first couple of years, yes, you are carbon negative under any of these injection scenarios. But there's a point at which you start becoming carbon positive because all this stuff starts to creep up on you, and it really, takes over in terms of the CO2 emissions. They also, considered different gas separation technologies here. Which has a minor effect, but really the injection scheme, will give you, depending on what you're doing, it gives you anywhere between about, 10 years to maybe 4 or 5 years where you truly are carbon negative. And then you end up being net carbon positive. So you have to be careful about how you design these projects. But I think this is, kind of an intriguing result if we go back to this, discussion of if we're going to continue using fossil fuels in a net zero carbon world, how do we abate those CO2 emissions? And this is one way of doing it. So interesting stuff. Okay, now we do need to talk about the economics of all this because this is kind of a big deal. So depending on where you are injecting and where you get your CO2 from, the cost can vary over several orders of magnitude, okay? So it's anywhere from if you are, injecting into like a saline aquifer, you're looking at, tens of dollars per ton of CO2. But if you are specifically looking at like doing direct air capture and then injecting that into peridotite, which is a type of ultramafic rock that will react quickly with CO2, depending on how hard you have to pump and how much you have to compress the CO2, you may be up in the thousands of dollars per ton of CO2. So there's a very wide variation. But if we just think about if we want to sequester all of the carbon dioxide that is currently in the atmosphere, so remember that was about 3 quadrillion kilograms, that would cost you about $33 trillion in sedimentary reservoirs. And then up on this high end here, it'd be, 132 trillion to 16 quadrillion dollars. That's a lot of money, okay? I don't know if that's maybe what we want to be focusing our efforts on. But if you think a little bit smaller, and I think it's not reasonable to expect we're going to remove every single molecule of CO2 from the atmosphere. But if you just think about energy-related CO2 emissions in 2021, that's a smaller number. If you want to inject all of those into a sedimentary reservoir, you're looking at $36 million a year, which is actually not that much in the grand scheme of things. And even doing direct air capture into peridotite, you're looking at 144 to $18 billion a year. So these start to come down to numbers that are tractable in terms of what could be spent on this. But the real problem is that if you're a company and you want to rely on the market to do this, there has to be some monetization of the carbon that you're storing. So, I looked this up. There's an interesting study by Greenstone and Nath where they came up with these figures of between $130 to $460 to what they call abate a metric ton of CO2 in the United States. And they did this by actually looking at changes in electricity prices associated with switching to low or zero carbon energy sources. And so that's kind of our ballpark figure for, per metric ton of CO2. It's, in the hundreds of dollars range. Now, the Inflation Reduction Act has this 45Q tax credit, which gives companies credits for carbon storage. And there's kind of a sliding scale depending on how they capture the CO2 and then what they use it for. And so for enhanced oil recovery, you get $60 per metric ton. The thinking there is, if you're doing this for EOR, you're already making plenty of money from the oil that you're selling. So we'll give you a little bit of an incentive to do that, but with the understanding you're profitable from other things. But on the high end here, we're looking at $180 per metric ton for subsurface storage for CO2 from direct air capture. And so that starts to become a situation where it could be profitable for companies to do this. If you couple that with what some of these companies like Heirloom are doing, which is they're selling carbon credits to large carbon emitting industries, then that could become a business model. So I think we'll see how that plays out in the future. It's still early days in terms of this. Another option is what we call cap and trade. And so the way cap and trade works is that if you're an emitter of CO2, like a utility who has gas-fired power plants, you will be given a certain quota of tons of CO2 you can emit. And if you exceed that quota, then you have to pay a fee. But if you do not exceed that quota and you have extra CO2 that you could be emitting, you can sell that to companies that are exceeding their quota, or you can trade them for other things. So you're basically creating a marketplace for CO2 emissions. And there are some of these kind of regional markets that do this. There's one on the U.S. East Coast called the Regional Greenhouse Gas Initiative, which attempts to do this for a lot of the electricity generation there. And the allowances here, it's about $6 to $25 per metric ton of CO2. So that's much lower than the projected cost of abatement, but it is something to try to create an incentive for companies to dial down their CO2 emissions. So, again, we'll see where this goes, as decarbonization efforts proliferate. But it's, like I said, still early days. So the take home here is that our tax credits and cap and trade might be getting to a point where this could be cost effective. But I think we're still in a situation where you can't make money just doing carbon storage. You have to have something else in your business that is making money. That's just the way things are right now. So, the utilization aspect is intriguing, but we'll see where this goes. Okay. Any lingering questions about CCUS? All right. Well, let's go ahead and get started with the project. I'm going to stop zooming here.